Okay, good afternoon and welcome back. So this morning we had the mini course by Dieter. One thing I forgot to mention is that this mini course will continue for those staying around next week. So the mini course that's about to start is also going to continue to the next couple of weeks. So today we have the pleasure of having Keith Levin. He's going to be our lecturer for week 1. And for the next 2 weeks, we're going to have Jesus Arroyo and Joshua Cape as our lecturers. And they'll be, so this week's, Keith's mini course is called Introduction to Statistical Network Analysis. The other ones are called Statistical Network Analysis, so you get the idea. And without further ado, please, Keith.
Thank you, Roberto. Primeiramente, muito obrigado aos organizadores, a Andressa, a Roberto, a João. É uma honra estar aqui. Isto é quase todo do meu português, sim? Então, vou mudar a inglês agora. Okay, so I hope I didn't embarrass myself too much. That's about all the Portuguese I've got. I'm sorry. But a genuine thank you to the organizers for the invitation and for setting everything up. And thank you so much to the staff here. You've done just a wonderful job. So I've been tasked with running a 4-day short course here that is titled something like Introduction to Statistical Network Analysis. So the old saying is like a person cannot serve two masters. I'm going to channel Luc Devroy and to quote him the other day, hopelessly try nonetheless. So I have kind of 2 goals here. One goal is to present kind of the very basics of the problems that we care about as statistical network analysts. So statisticians who study networks rather than probabilists. On the other hand, most of this audience are probabilists, and so one of my goals is to show you the problems that we're kind of stuck on, right? Or to illustrate why our problems are hard. It is also my goal to give just enough of a survey this week that, if you're only here for the week, you'll come away with some kind of a flavor for the problems we care about. And on the other hand, if you are sticking around for the rest of the workshop, you'll be set up well to hit the ground running with the course that will be taught by my dear friends Jesus Arroyo and Joshua Cape. So that'll be the following weeks from now. One other thing before I dive in, so English is my native language, and so I have the habit of I'll get animated and start speaking quickly. As someone who tries to learn other languages, I understand that can be annoying. So if at any point I start speaking way too fast, or you're like, what, you want me to slow down? Just wave your hands frantically or something, make a gesture, I will understand. Okay, now a bit of audience participation. There are 2 places we could begin. One is to kind of pick up where Dieter left off, and we can see a little bit more about the Erdos-Renyi random graph. I get the sense that most of the audience here is familiar with first and second moment methods, but a major tool I want to talk about this week is going to be concentration inequalities. And so maybe a show of hands, who would like to see more detail on how those methods work? I think for the most part everyone gets it, but there's no shame. This is the problem. Now you're basically asking people to raise their hand to be like, I don't know a thing, and no one likes to do that in front of academics. So maybe to the grad students, if I can teach one lesson to people, I'm not sure I'm senior enough to do that, but it's fun to be wrong, because then you get to learn stuff, right? I'm wrong all the time, very publicly. I will say wrong stuff up here just by accident, right? There's no shame in saying yeah, I don't know a thing. So let's try again. Would we like to see more detail on first and second moment method? Okay, and then votes against, who are just I never want to see that stuff again. All right. Okay, that was pretty even, honestly. So, oh boy. Okay, tell you what, those of you who want to hear more about first and second moment methods, one, I should say while I'm thinking of it, I'm going to post lecture notes accompanying these lectures, both on my website, and I will send them to one of the organizers. They'll be available to you. Those notes include a detailed treatment of first and second moment methods as applied to a different phase transition in the Erdos-Renyi random graph. And I think we'll start today talking about kind of the next most complicated model, where we already kind of don't know anything, namely the stochastic block model. So, and I promise we'll keep things today very light. We all just had lunch. Everyone's still easing into the afternoon. There's going to be almost no math today. We're just going to set up some models, and then in the following days, we'll talk a bit about how we prove things in those models and what are the kind of big open problems. So without further ado, so we heard this morning about the Erdős-Rényi random graph, and Dieter acknowledged near the end of his lecture that while this is a nice probabilistic object, right, if we care about combinatorics, it's kind of the natural place to begin. If I want a model of networks that actually looks like the real world, right, if I generate a network from this model, I would like it to resemble the networks we see in the real world, right? The Erdős-Rényi random graph is not a very good model, right? Why? Well, for starters, in the Erdős-Rényi random graph, every node kind of looks the same, right? Every vertex behaves the same way, right? Is that true in the real world, right? Like, let's just think about Facebook. Does everyone have as many followers or as, like, I don't know who's famous on Facebook now. No one uses Facebook anymore, so I have no idea, right? I don't know. When I was the grad student stage, it was Justin Bieber. He had, like, all the followers on Facebook and Twitter, right? And I don't know if he's even still on any of these platforms, right? But, like, not everyone has 1 billion followers on Facebook or whatever, right? Most of us have 100, or some of us aren't on Facebook and have 0, right? So we'd like a model that somehow captures the fact that vertices, nodes in real-world networks behave differently. Okay? Now, the first model we're going to see here, the stochastic block model, does that in kind of the silliest way possible. It says, OK, instead of all vertices behaving the same way, there are k different ways that you can behave. Those correspond to k communities. So let's write down the model here. Throughout the week, I'm going to denote the edges of a graph G VE. So I'll always identify V here with just the integers 1 to n. And I will interchangeably refer to G and its adjacency matrix A. So A here is a matrix. Okay, and Aij equals 1 if I forms an edge with j, and 0 otherwise. Okay. So in the Erdős-Rényi random graph, A is a binary symmetric matrix, and all of its entries are IID coin flips. Okay. In the SBM, we're going to say the following. So SBM stands for stochastic block model. Okay. This model was originally due to Holland. Always misspell this name. Maskins. And let's see. In 1983. Right. Okay. So here's the idea. Instead of all of these entries of A being IID coin flips, we're going to say that 2 steps. 1, assign, tau 1, tau 2, blah, 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 up to tau n are going to be labels from 1 to k. So every vertex gets a label in the set 1 through k. Okay? These could either be, say, drawn IID from some distribution, or maybe just specified. And we'll come back to that point a number of times this week. Okay. For now, just imagine there's some set of what we're going to call community labels tau. Okay, so every vertex belongs to a community. The ith vertex belongs to community tau sub I. So again, k communities, 1 through k. Every vertex is assigned to one and only one community, and we'll store that community membership in tau here. Okay. Then, conditional on tau. And sorry, this tau here, just the vector of tau 1 through tau n. Aij are drawn independently as Bernoulli random variables with probability b sub tau I tau j, where b here is going to be a big matrix of probabilities, well, not that big, k by k, and it'll be symmetric. Okay? And when this is the case, I should start writing a little smaller so that we don't use all the board in 10 minutes. But when this is the case, I'll write something like A distributed as an SVM, matrix B, and tau. Okay, so that's the basic setup. Okay, so what have we done that kind of changes things from the Erdős-Rényi random graph? Well, we started with all nodes being the same, and now instead there are k different types of nodes. Okay? So if you want to squint and like wear your statistical physics hat, this is something like a k-spin model or something like that, and there are connections to Ising glasses and things like that, way outside the scope of this course and my own expertise. So I'll just mention that there's a connection and happy to talk about that offline. All we've done here is we've said, okay, well, instead of just one kind of vertex, right, we have k different types. Okay, so roughly speaking, if we're thinking of modeling, say, a social network, we're imagining that every person belongs to like one of k different groups, right? Like there's the, I don't know, the computer science group, there's the math group, there's the sociology group, and so on. And once I know what group you belong to, once I know your the value of tau, I know exactly how you're going to behave stochastically, right, on average. Okay, any questions so far? Awesome. Now, depending on the application, we might want to estimate either B or tau, right? So our goal is going to typically be estimate B and or tau, right, from A. Right? Our collaborator in some discipline or other comes to us and says, hey, I got this network. What can you tell me about it? Right? We are going to take that network and pass it through some kind of an algorithm, and hopefully out the other end we get an estimate for B and for tau. Right? This is maybe a good time to pause and highlight what I think is an important distinction between like pure probability and statistics, which is, can we be charitable and call it applied probability? I don't know if that makes people angry or not anymore, but our goal here, right, is not necessarily to say, you know, if I draw A from the SBM, how does A behave? I mean, it's useful to know that because it's going to allow us to do things like what's called goodness of fit testing, right? And I'll talk about that more later in this week, right? But our goal, first and foremost, as statisticians, is to understand how to, from data, right, from our generated random variables, right, recover model parameters. The hope is that B and tau tell you something about the world, right? If I can apply an algorithm to A and out the other end come guesses as to tau, I know something about the community memberships, ostensibly, of the vertices in network A, right? So, right, probability theory tells us everything about going from this model to A, right? Statistics, we care more about going from A back to a model, right? Inference. Right? So we want to estimate B and tau from the data, rather than saying, okay, if B were such and such, how would A behave? Okay. So let's just note, okay, if I knew tau, so if I knew what community every vertex belonged to, then I would, you know, then B would be easy. Right? If I knew what all the community memberships were, I could come up with a very simple estimate for B, right? Like the KL entry of B, just for example, right? Say B hat, our estimate of B, KL, could be all of the I. Let's do this. Okay, if you told me tau, it'd be a very simple estimate for B. I'll just look at all of the vertices that are in, say, community K and community L, and count up what fraction of the possible edges between those two groups are present, right? Okay, and if K equals L, then this turns into a binomial coefficient, but same basic idea, right? Okay. So, roughly speaking, the hard part of this problem is figuring out tau, right? Like if I know tau, then B would be easy. Okay. Now, this is the very high level intuition behind, this is the kind of rough intuition behind the EM algorithm. That's the expectation maximization algorithm. I'm not going to say much about that here, but I believe Jesus is going to tell you about that in the coming weeks. Is that correct? Okay, good. I didn't want to like promise something and then Jesus is like, no, I'm not talking about that. So Jesus will talk a little bit about this during his lectures in the coming weeks. But for now, if you've heard of the EM algorithm, the expectation maximization algorithm, right, this is the basic idea behind it, right? If I knew tau, I could guess B, right? And so I'm going to just repeatedly like guess tau, estimate B, guess tau again, right? Another important thing to point out, because it just is going to come up again and again this week, is that this model suffers from what's called the non-identifiability. So in statistics, right, our problem is always that I want to go from data, I want to go from A, back to guesses as to the model parameters, right? So I want to find a way of mapping data to estimates of my parameters. And it would be a big problem if the same data, right, corresponded to more than one model parameter, right? So let me give an example here. So let's pick some permutation sigma in Sk, just the set of all permutations on the integers 1 to k. Okay? And if I apply sigma to the entries of tau, and reorder the rows and columns of B, right, then, and I'm going to write this, like, don't take this statement too literally, but it should be clear what I mean by it. The probability of some particular A, let's not be Bayesians here, parameterized by B and tau is equal to probability A. Let's write this as like sigma of B, sigma of tau. Okay, and by sigma of B, sigma of tau here, I just mean relabel, right? So my original tau was like a bunch of numbers 1 through k. I'm going to apply that permutation of those numbers, and then I have to do the same permutation on the rows and columns of B, right? Suddenly, these two probabilities are the same, right? Once I fix B and tau, I can shuffle the labels any way I want, and the probability doesn't change. Okay, why is that a problem? That means there are two different choices of parameters that give rise to the exactly same likelihood, the exact same probability of any data, right? So any procedure I have that tries to tell this model apart from this model is going to fail. There's no amount of data I can see that will tell these two models apart. Okay, so this is a non-identifiability. Okay, and as statisticians, we worry about this a lot. If you ever interact with, there's like a subfield of epidemiology that deals a lot with, like they fit SIR models and things like that. They're also very obsessed with this for good reason. Like you don't want to run a giant public health study and then have like some estimate pop out and be like, I don't know, there are 3 different public health interventions we could make, and I don't know which one to use. That would be bad, right? Okay, so this is a non-identifiability. Those of you who are familiar with the label switching problem, in like mixture modeling, for example, in like KGMMs, things like that. Same problem, right? I can take a mixture model, I can take a mixture of Gaussians, and swap the orders of the cluster labels, and nothing has changed, right? Okay. So normally, statisticians are very bothered by this kind of problem. Lucky for us, we don't really care that much in this situation. Why? Well, if you hand me a network and I hand you back a clustering of the vertices, the thing you care about isn't what number I assign to the vertices. Like, I don't care if this cluster is cluster 10 or cluster 50, right? What I care about is the partition of the vertices that it corresponds to, right? So this is an example of a kind of non-identifiability it's annoying. We're going to have to keep track of it in a lot of these models, right? But it's not going to stop us from doing the things we care to do, right? We can still perform like network clustering nonetheless. Okay, so good time to pause, right? I state this thing just to like as an aside, part of my job here is to be an ambassador for statistics to probability and combinatorics. And I don't know whether I'm the right person to do it because my PhD is in computer science and I was advised by a statistician and a probabilist. So like, yeah, I'm not sure I'm actually the person for the job. Maybe yes, because I lived among the probabilists for a time, right? But like part of my job this week, in my view, is to throw a bunch of statistics concepts at you so that we can kind of find like how do we bring probabilistic approaches to some of these problems that we're stuck on. Right? Okay, so like non-identifiability is a problem we're not really stuck on. We just don't work with models where this happens. We assume it away somehow or other, or we convince ourselves that it's not a problem. Right? Here, we don't care. I'm interested in how tau partitions my data. Okay. Now, let's suppose that tau here are the true community labels for the network that I observed. So I'm going to see a network A drawn from a stochastic block model. So I'm just rewriting that same model over here. And let's say that I come up with an estimate for tau. Say tau hat, which is going to be like a function of A somehow or other. Okay, and again, this will be in k to the n. Okay, just as an aside, I'm going to assume, at least for today, that magically we know this k, which already, like if you're a statistician, like remember, you don't get to know what model things came from, you just get to see A. What the heck should k be if you just hand me a network, right? So I'll talk a lot about that problem, or rather I'll refer to that problem a lot until like the last lecture when I'll actually talk about the problem. In most of what we're going to talk about these first few days, I'm just going to assume that magically, like a wizard appeared out of nowhere, told us k, and nothing else. Like, okay, we'll talk later about this model selection problem where I have to pick k based on the data, right? That we don't have a choice. But for now, we're going to imagine it's known. Okay, so I know k, and I feed a into some algorithm, and out comes an estimate of tau hat. Okay, how do I know if my estimate is good? So, question. Is tau hat good? Okay. Now, there are a number of ways that you can assess that question. The simplest one, and the one that we'll just talk about today, is simply called the agreement. So A of two clusterings, tau hat and tau, is going to be a maximum over all permutations sigma in Sk, and then I'm going to just average over all of the vertices and ask whether, after applying that permutation, did I get everything right? Okay? So again, assessing how well tau hat recovers tau, I need to account for this non-identifiability, right? We need to be generous to this estimator and not penalize it for picking the wrong ordering of labels, right? Like if I have two communities and like I call, in my estimator, I call community 1, community 2, and community 2, community 1, we don't really care about that, right? So this is going to say we're going to take the most charitable relabeling, right? Where what we like is to have the largest fraction possible of our estimates agree with the truth. Okay? So again, this is called the agreement. Okay. Just a couple of notes here. So, okay, this is fine. Who here like actually runs experiments? Like if you're a statistician, hopefully you do, right? Like you run experiments on computers. If you have to actually implement this, like, oh no. Okay, it's not a problem. I mean, it's a problem in a funny way, but it's not really a problem. So we can solve this maximization via the Hungarian algorithm. So I believe we've now had, was there Hungarian roulette yesterday? Is that the term I heard? And now we have the Hungarian algorithm, so someone else has to do a Hungarian something. I don't know anymore. So this is a paper due to Kuhn in 1955, I want to say? Yes. Okay. He didn't call it the Hungarian algorithm. Later authors called it the Hungarian algorithm, I think because Kuhn and some of the other authors who were first studying this were Hungarian. I also want to note, just as a fun curiosity, a couple of historians of ideas have actually gone back and found pretty convincing evidence that actually Jacobi solved this problem before anybody else in like 1895 or something ridiculous. So I don't know for sure whether that's actually true. I didn't go and like read the original Latin or French or whatever he was writing in. But maybe just a fun aside if anyone likes to dig into these things. I'll also mention the Hungarian algorithm generally requires order cubic time in the size of the input. So if k here were big, we might start to have an unpleasant time, right? If k is a couple of thousands, then things are a little wonky. There are speed-ups for this that require things like sparsity in what's called the cost matrix. Again, this is just an aside for the people who like optimization, right? So this maximization is expensive typically if k is really big, but most of the time k is going to be like 5, 10, 20, 100. Like it's not going to be in the thousands, so we don't usually have to worry about this. Okay. Now, in classical statistics, we think of the parameter that we're trying to estimate as being some either like scalar or some finite dimensional object. And as we get more and more data, like that object stays the same size, and therefore we get like more and more accurate estimates of it. That's not quite the case here, right? Our parameter of interest is tau, and tau grows in n. So we need to be a little careful when we talk about the consistency of tau hat, meaning in what sense does tau hat recover tau? Okay. So if you go to the literature on this, there are kind of three, arguably four, different notions of consistency here, what it means to succeed asymptotically at this problem. I'm going to make just enough space over here by moving the word algorithm to over here. Okay. And so we'll make three basic definitions here. So three different ways you can do well at this problem. And again, there's a fourth, and on most of this, I'm following this fantastic survey by Emmanuel Abe in JMLR from 2018. So this is all treated in much more detail there. So there are three notions of consistency here. The first is called strong consistency. Okay. And basically what that's going to correspond to is that in the large n limit, I will always recover all the vertices. Okay. Then, okay, that's often a little too much to ask for. There's weak consistency. Okay. In the large n limit, there exists a sequence of alpha n's such that in the large n limit, I'm sorry, let me restate all of that written nicely. There's a sequence of alpha n's. Those alpha n's are in 0, 1, and they increase to 1. Okay, so there's going to be a series of numbers, like a series of proportions getting bigger and bigger. Okay? And we're going to ask that if we replace this 1 by that sequence of alpha n's, right, that probability goes to 1. Let me write it out. It'll be more obvious. Such that the limit as n goes to infinity okay, so right, we've weakened this requirement that we correctly label all of the vertices to just saying we're going to get an increasing fraction of them. Right? Said another way, right, in the large n limit with high probability, right, we're going to recover an increasing proportion of the vertices. Right? And for n big enough, that proportion of the vertices will get arbitrarily big. Okay. There's a third condition, maybe the one that those of you who have seen this area before are most familiar with. Okay, and that's called detection. And I want to voice a mild complaint with this name because community detection sounds like you're just saying, like, is there a community structure or not, right? Like, I hand you a network and you tell me, are there one or more blocks, right? Like, is it an Erdős-Rényi random graph or are there more blocks? Is k bigger than 1? That's not what this is, right? Okay, what this is that you can recover tau at a fraction bigger than chance, okay? So I don't know actually who is responsible for this name, and I'm sorry if I offend whoever is responsible. Like, it's not ideal, but it's fine. Right? I guess this is like having opinions about asymptotically almost surely versus with high probability. Right? We all can complain about these things. Okay, so what is this condition that there exists some positive epsilon such that limit of the probability that I detect more than a fraction 1 over k. Okay, so in the large n limit, right, I eventually, with probability 1, excuse me, with probability approaching 1, I can do some amount better than chance, right? Chance would just be guess everything, 1 through k. Right? Okay. So there is one. Oh yeah, question. Yeah.
I guess it's worth mentioning about the names that the first two things also have another name.
Yeah. Thank you. I was about to get to that. So you go and read. If you read the literature, there's kind of, I don't exactly know how these two camps break down, whether it's some historical, like statistical physics versus statistics or something like that. But yeah, you'll see elsewhere these are called, so it'd be like strong recovery, weak recovery, things like that. So you see the terms recovery and detection, right, and consistency all used a little bit interchangeably, right? There's one condition stronger than this, and it would be to say, eventually, almost surely, you recover everything, right? So with probability 1, there exists an n after which a of tau hat comma tau is 1, right? If time allows, at the end of this week, I will present a method for doing that with some caveats, that namely that method is not optimal in some domains. And we'll talk more about that in the rest of this lecture. Yeah. Okay, so all right, now we have to decide on a piece of board to erase, and maybe we just start back at the beginning. So I'm going to state a result. We definitely don't have time to prove it, and its proof is sort of, I mean, it's a very interesting proof, and I'll point you to where you can see a very nice presentation of it in Abe's survey, actually. I want to state the result just because it's like kind of a triumph of probability theory that we know this about this model. And it's going to sort of hint at, why we might hope that we can like solve this problem on real data, right? So basic question, under what conditions can we achieve these different notions of recovery, right? When can we estimate tau? Okay. I'm just going to state a representative result here, right? There's like 15, 20 years of papers on this. And again, Abe's survey is a great place to look for, I mean, I guess it's now 6-ish years out of date, but still a good place to start. So I'll just state a representative result. This is a combination of a few different results. Massoulier, 2014. And then a pair of papers by Mossel, Neiman, and Sly. In 2015 and 2018. And again, all these citations will be in the lecture notes that I'll be posting, so don't feel like you need to go Googling for things now. Like actual citations with like paper titles are available. Let's imagine a special case. K equals 2. Okay. And so I'm at 2-block SBM. There's 2 communities. And B11 equals B22 equals P. And B12 equals Q. Okay, so P, Q in 0, 1, and they're going to be fixed. Oh, and I'm so sorry. This should be, very sorry, P over N and Q over N. So P and Q are fixed in 0, 1, and then my matrix B is being kind of pushed towards 0 at a rate like 1 over N. Okay? So again, just to reiterate the correction, I initially just wrote P and Q here. It should be P over N and Q over N. So our matrix looks like, and right, I should say that like there are 2n vertices here. Okay. So this looks like P over N times the n by n matrix Q over N times n by n matrix, and so on. Okay, and so Jn here is like the all ones matrix n by n. Okay, so our 2 blocks are equal sized. That means we're in a balanced SBM, right? The 2 communities are of the same size. Okay, and as n grows, the B matrix is getting closer and closer to 0. So it's kind of harder and harder to tell B apart from the background, from just 0, and harder to tell P and Q apart. Okay? And let's define a signal-to-noise ratio quantity, P minus Q squared over 2 times P plus Q. Okay? So like roughly speaking, you're comparing like half the squared distance between P and Q against kind of like what's the overall number. Yeah? Not necessarily. So the question was, is P necessarily bigger than Q? And the answer is it doesn't have to be. Mm-hmm. Yeah. We'll talk more about that. I think we'll get to it today. Right? I mean, as like the very brief aside, right? P bigger than Q corresponds to the on-diagonal blocks here being bigger probabilities than the off-diagonal. We call that an assortative model. Right? You're more likely to talk to people within your community than outside. Right? Assortative meaning you sort with your community. Okay. And like there are situations where actually the assortative case is like easier than the disassortative or sort of mixed case. But here we need no such assumption. P can be bigger than Q, P can be smaller than Q. Heck, they can be the same. It's just that like you won't be able to do anything. Right? Okay. The result here is that detection is possible. If and only if the SNR is bigger than 1. Just as an aside, this quantity is called the Keston-Stigum bound. I'll put the name here. This is in reference to a paper from the 60s on a problem called tree recovery. The problem is basically you have, you imagine like the nodes on a tree, and you see the order in which they receive some message. And that message started from the root, okay, and was kind of broadcast over the edges of this tree. And your job is to recover the root of that tree. Okay? And it turns out you can show basically that you can kind of reduce the problem of estimating tau here to performing that tree recovery problem. So it's a really beautiful result, very nicely presented in Abe's survey. We definitely don't have time to go into it here, and it's not really, like maybe it's something that Dieter wants to talk about. It's you know, it reaches a point of not being statistics anymore, it's a probability proof, right? So beautiful proof, worth reading, but my job here is to mostly talk about statistics and not probability, so we'll just kind of mention that that's where the proof comes from and leave it at that. Another remark is just that, so in this problem, this doesn't happen, but the SBM in this kind of recovery problem is a nice example of where we have what's called an information computation gap. Okay? So the idea here is that there are going to exist domains for certain problems where signal is present in the data, right? Like if I gave you A, provably there is signal present in A. But there is no polynomial time algorithm that can actually identify that signal and use it to recover, say, tau. Okay, so I want to stress that doesn't happen here, right? I should say detection is possible and is like computable, right? Is like, I don't know, efficiently computable. Efficiently computable. Okay, so everything's fine here, but I want to stress that there are, like, you don't have to make this problem much more complicated for this to become so hard that, in fact, there's a gap between when you can find the solution, like when the solution is present statistically and when you can actually identify it in, like, before the heat death of the universe, right? Okay. All right, so I'm going to take a moment to erase a little bit. And what I want to talk about next is, so we've established that there are situations where we can estimate in this model. And I'm going to leave this here just so I can point at it again, but I'm going to take away these two here. So I'll give everyone 1 second to frantically write down things if they need to. I see no one panicking. So. Okay. So we've established that there exist regimes where recovery in this model is feasible. And the next question should be, how exactly do we go about performing that recovery? And this is a very well-studied problem, and so there's a lot of methods out there for doing this. I'll mention 3, and I think you'll see a little bit of at least one of them next week. So right, maybe like how to recover tau. Okay. So one option here is you can cast this as what's called a semi-definite programming problem. Yes, of course.
Is the detection algorithm there something kind of simple, like you just sort by?
Great question. So it depends on how far apart P and Q are. If I think in this regime, just sorting by degree. So sorry, I'll repeat the question. The question was, can I do something silly like just like look at the degrees or something like that? And so here the answer is no, just because like all the degrees are going to be about the same. Generally speaking, if P and Q here are constant, I believe the answer is no. Like there's no kind of silly like look at the degrees or just look at individual vertex behaviors. That's off the top of my head, right? And I want to stress like this is not my main area, right? I know about these things because like I work on networks and you're required to. Like vaguely know this, right? But off the top of my head, I would think that none of the kind of obvious things work here. So in fact, like this is kind of in the hardest, like this is the hardest regime, right? So typically, when we think about network modeling, we're not going to imagine that we're this sparse, right? Like in this model, like all your degrees are like at best maybe like They're basically like a constant, right? Maybe log n if you want to be really generous. So, yeah. So like that's going to be one of the kind of like sneaky things we're going to do at some point is say like, this is too hard, but it's also a little unrealistic anyway, right? And so we'll pass to a model where, one, there's going to be a lot more structure, right? But two, that structure is going to be something we can kind of like latch onto and do estimation without having to think about like information theoretic bounds. Great question. Okay. So one way to solve this is with semi-definite programming. So this is not an optimization workshop. I will just state that semi-definite programming is sort of the matrix analog of linear programming. Okay? So instead of working over, say, all like vectors and try to maximize some kind of like, vector product with something else, I'm going to maximize some function of a linear function of a positive semi-definite matrix. Okay? The very high level idea here is that I'm going to encode tau here in a big matrix Z. Its rows are going to encode the memberships of our vertices. Okay? And then I'm going to try and basically bake into this objective something like a likelihood, okay? Very roughly speaking. We're going to come back to that idea a little bit. I think we can get to it today, and when we do, I'll gesture back to this, right? But like, I just want to basically say the name, and I'll mention that there's a paper developing this by Arash Amini and Lisa Levin, 2018. Okay. Another option here is to apply, okay, so if you're a computer scientist, this is belief propagation. If you are a statistical physicist or statistician or basically anything else, this is approximate message passing. If you did your PhD in a computer science department and now you're in a stats department, you don't know what you call it, and so you just switch back and forth based on a true story. So again, we could spend an entire week talking about these tools. The very high level idea, again, is to treat this, this kind of goes back to work in like 2000 to 2010 on graphical models, right? So if I can write down a graphical model on my variables of interest, there exists a family of algorithms called belief propagation that allow me to maximize the likelihood, maximize probability of data under those models, provided that graph has a nice tree-like structure. And the basic idea behind what we were calling loopy belief propagation when I was a grad student, and now I think we just call belief propagation and accept that like it's always approximate. Like you can run these algorithms even on graphical models that kind of don't have this nice tree-like structure. Okay? And the magic is that it converges to something nice most of the time. Okay, so I think the kind of canonical paper on this is by Abe and Sandin in 2016. I'll also mention well, we'll come back to that. Yeah. Okay, so the paper where they actually did this for specifically SBM is Abe and Sandin, 2016. There's a much more general textbook by Mezar, Montanari, and there's a third author whose name is escaping me at the moment. That's kind of more generally about some of these methods. And again, just kind of outside the scope of what we're going to talk about this week, I just want to mention that again, like, I'm going to speak almost exclusively this week about like one family of methods. I don't want you to take away from that like that's the only game in town, right? So I'm kind of going on about these other options because otherwise you're going to get a very biased view of like what we do in network analysis. Okay, another option here would be something like, again, we mentioned the EM algorithm earlier. Okay, or kind of relatedly, variational inference. Whoops. Variational inference. I mean, if you have questions about that, like a world expert is here in the room with us. Andresa has a couple papers related to this. And then I'll also say, like, how do I denote, like, we're going to look forward to Jesus's lectures later in the week, right? So, like, or next week. Okay, so a few different ways we can do this, right? You can write down a likelihood for this model and then try to maximize the likelihood of your data, right? Maximize the probability of seeing your data under a particular set of parameters, right? You can do that with the EM algorithm. You can do something kind of related with semi-definite programming. You can do something still kind of in the same family with belief propagation. These are all good, right? I want to talk mostly this week about another family of methods. These are called spectral methods. Okay. And, well, the name is somewhat self-explanatory. The intuition is going to be that information about community structure here is going to be carried in the eigenvalues and eigenvectors of the adjacency matrix A. I guess over here, right? So I'll write here kind of intuition. Community structure is carried in the eigenvectors and eigenvalues of A. Okay, and I'm going to apologize in advance for the fact that I just habitually write evex and evals for eigenvectors and eigenvalues. You would too if you wrote those words all of the time, right? So anytime you see that, I don't mean like we're evaluating something. I mean eigenvalues. Okay. I should also acknowledge that, like, so I was raised in a family of engineers, and so I was taught to write in all caps because that's, I guess, what you did back in the day on like drafting paper or something like that. That's supposed to make reading or writing easier to read, but I think my handwriting has devolved to the point where like that's not true anymore. So if anything I write is not clear, just like raise a hand. I'm not sensitive about this. Right? Okay. So we've already heard a little bit about these ideas this week, right? Before lunch, Luke told us about how, like, there's some interesting behavior of the leading eigenvalue of the adjacency matrix of certain trees, right? We heard yesterday about how, I think this was during the open problems session, we were talking about how the second eigenvalue of the Laplacian matrix, which I'll mention at least briefly here in a moment, carries information about relaxation times of random walks. Okay, so the spectrum of A, or matrices related to it, like the random walks matrix, if you've heard of that, or the Laplacian, and again, I'll talk more about those this week. Right? The spectra and eigenstructure of those matrices carries information about the structure of the network. And so spectral methods seek to use that structure to make inferences about B. Okay. I'll mention just kind of like there's an entire subfield of graph theory just devoted to like questions about the spectrum. I'll mention two especially good references on this. So Fan Chung has a very famous textbook in 1997. And then more recently is Brouwer and Hammers. Like 2011. Okay, more recently in the like charitable sense, I don't know. Okay. So again, like this is understanding how the spectrum of A reflects structure of A is an entire subfield of graph theory. We draw on only a tiny bit of it to do statistics because again, most of the time, like the structure you're looking at in A is a very fine structure that ends up being lost when you like add any kind of noise to A. But nonetheless, the intuition behind why some of these methods work comes out of this work. Okay. So why should this work? Right? So let's get an intuitive example here. Let's go back to this. And I'm so sorry. I realized that I wrote something very silly to you all. So this J isn't supposed to be here, right? This guy's supposed to be 2 by 2, right? Yeah, Roberto's nodding vigorously and like didn't correct me. So, right, so I'm so sorry, right? This should just be 2 by 2. The matrix I'm about to draw for you should have those J's there. Okay, so again, a correction. I wrote a bunch of capital J's here, meaning like the n by n all ones matrices. Of course, that's wrong, right? The B matrix is supposed to be k by k, and k here is 2, so this is just a 2 by 2 matrix. Sorry for the error. Now I'm going to write the matrix with the J's in it, and that's going to be the expectation of our adjacency matrix if we make one particular assumption. Okay, so bear with me a moment. So, example. Let's assume, this is an assumption we never get to make in real life, but let's assume, for the sake of illustration, so we have 2n vertices, and we have tau 1 equals tau 2 equals tau n equals 1, and then tau n plus 1 equals everything up to tau 2n equals 2. So I've sorted my vertices so that the first n are all community 1, and the remaining n are all community 2. Then the expected value of A, and I want to stress this B is that B over there. Okay? This equals now P over n times, just P over n times all ones matrix, Q over n all ones matrix. Right? Okay, so I basically took B, right, which is 2 by 2, and I blew it up to be 2n by 2n, right? I get n by n copy of this guy in the top left, n by n copy of this guy in the top right, and so on. Okay? All right, why did that help us? Well, this matrix has 2 eigenvalues. Right? Those eigenvalues are p plus q and p minus q. Right? And then its eigenvectors up to renormalization are u1, like a matrix of all ones. Okay, so this is an R 2n. So what I mean here is just a vector of n1s and another vector of n1s stacked on top of one another. Okay? And the second eigenvector is orthogonal to that. Okay, up to renormalization, like later on we'll care a lot about are these unit norm or not, but it can be fast and loose for now. Okay. So, in particular, if I had access to this matrix, right, I could read the community structure off of it, but I don't even need that. All I need is the second eigenvector. So all I need to see is this second eigenvector. So if we knew U2, we would be done. Right? We just literally read off of the elements of U here. And that would still be true even if we didn't live in this magical world where like the vertices were already sorted for us, right? You can imagine, like well, real life is in quotes here because this is still like there's no noise on this thing, but right, you can imagine that someone gives us this matrix all jumbled up. I apply the same permutation to the rows and the columns, right? I can still figure out which vertex belong to which cluster, again, by just looking at the signs of U2 here, right? Okay. So we have about 15 minutes left. I want to use that time to kind of drive home how we're going to use the spectral information to recover the community memberships. And then I want to spend maybe 5-ish minutes talking about kind of next steps. What are we going to do in the next few days? Okay. So the key problem here we see A, right, not its expected value. Right? In the real world, I don't get to see, okay, in the real world, nothing's a stochastic block model to begin with, but like the network I get to work with is not this thing, right? It's this thing plus a bunch of noise. Okay? So the hope is that the leading eigenvectors of A will retain some structure from U1 and U2. Right? Like one thing I want to mention here is that in this very nice setting, U1 doesn't carry any useful information. This is actually connected to, if you've seen the Laplacian matrix, right? That's what happens. A leading eigenvector is always a trivial solution. That's only because we have this very nice block structure, right? In general, these first two eigenvectors would both carry some signal for us, right? So we really do want both of them in general, right? This is like a defective case in a way. Okay. So that's going to be the hope. And in possibly tomorrow's lecture, more likely Thursday, we'll kind of go through a detailed proof of why that should be the case. Okay? And okay, detail is in quotes here. Like, I'm going to wave my hand at some stuff that Jesus and Joshua will fill in the coming weeks. But like the basic tools we'll put together some tomorrow and mostly on Thursday. Let's fix some notation here just so that we can kind of wave our hands at where we're going to go next. Because tomorrow I want to extend this model a little bit. So before going into estimation, I want to show how this model can be extended in ways that I think statisticians find very natural, right? And in ways that make the SBM seem a little less clunky, right? So I want to set up some notation now just so that we can hit the ground running tomorrow. Okay? And what I want to do in particular is kind of give a little bit of notation to help us write these kinds of matrices. So again, let's say that we have A drawn according to an SBM, probability matrix B, and community label is tau. Okay, so just remember that B here is k by k, symmetric, 0, 1, right? So it just encodes a bunch of probabilities. And now I'm going to build another big matrix here. And remember, I started waving my hands at this matrix Z when I talked about semi-definite programming. This is the same idea. Okay? I'm going to build a matrix Z. It's going to be binary 0, 1, n by k. So it has one row for every vertex in my graph. And I apologize for switching back and forth a little bit between n and 2n vertices. Right? 2n in these examples was just so that like I don't have to care about floors and things like that. Okay, how is this going to be constructed? It's going to be just, each row is going to be an indicator. Zik is 1 if tau I equals k, and 0 otherwise. Okay, so each row of Z is what we in computer science would call a one-hot encoding of the group membership, the community membership of vertex I. Right, so I look in the ith row, I find which entry is non-zero. That entry corresponds to tau I, the community membership of vertex I. Okay, why did we do this? Well, let's remember that A, ij entry of A is Bernoulli B tau I tau j. Okay, and that this guy just equals like Zi transpose B Zj. Right, where these Zi's and Zj's are like, I look at the rows of Z. Right, reasonably clear. Right, I just think of the rows of Z as these nice k-dimensional one-hot encoding vectors. Now I can just do inner products with B. The zi transpose B, zj just picks out the ij, excuse me, the tau I, tau j entry of B. Okay? And that means that the expected value of A equals z B B transpose. Okay. So I want to take a few minutes to hint ahead where we're going tomorrow, and then we'll call it a day, and we'll even end like a couple minutes early. These z's, in some sense, encode these like nice k-dimensional latent variables, right? Before we had this very combinatorial problem, right? I had to assign each vertex to one of k communities, right? And I'm still doing the same thing here, but now like Z is like a big matrix whose entries, whose rows encode these combinatorial objects. And I can even think now about the very natural relaxation of saying, well, instead of having the rows of Z be corners of a simplex, why not allow them to drift into the simplex somehow? Okay? That's going to be basically the theme of tomorrow's lecture. We're going to see how we can extend this model in ways that are, one, more realistic. And again, if you, I don't know, for some definition of realistic, right, we'll still have plenty of mean things to say about these models because statisticians are ever pessimistic about these things. Okay? We'll also see how, as we start to make that, that relaxation and start to think more about how to generalize this kind of a model, we're going to end up in a situation where it's very natural to associate to every one of our vertices a point in k-dimensional space. And then we can really think about networks that are driven by latent geometric structure. This is going to look a little bit like the random geometric graph that we saw this morning, except that our edges will not be deterministic. Right? You won't be able to look at how close were two vertices and immediately say whether they form an edge or not. It'll drive a probability. Okay, but there's going to be some nice connections to the random geometric graph. So the plan for tomorrow is going to be to pick up here and develop this model a little further. We'll see some of the models that have been kind of under intense study in statistics for the last 10 years or so. I'll wave my hand at some like interesting open problems, because as soon as you go to like generalizations of this model, a whole bunch of these like nice methods, like BP kind of stuff, start to get pretty nasty. So I think I'll stop it there, leave 5 minutes for questions, and you will not hurt my feelings at all if you immediately get up and go for coffee. Thank you all so much. I'll see you tomorrow. Don't clap. So questions, or you can just run to coffee. You will not hurt my feelings. Like, this isn't a like real question and answer, right? This isn't like, oh boy. Or we can just like, do I need to set the example and just like start walking away?
Yeah, but I mean, just make sure I understood the very last thing you said.
Mm-hmm.
So I guess one of your selling points for spectral methods that they're very general. I mean,
Yes.
They work for a variety of models and expect them to do well in many, many settings.
Yes, yeah. So I'll repeat the question that was faint praise, and I'll phrase it as a question. Roberto asked, Keith, is it the case that the reason we might like these spectral methods is that they're more general and kind of more expressive than models like the SBM? And the answer is, great question, Roberto. You're right. Yes, they are exactly that. So we'll see that theme again and again. This is a good time to acknowledge, though, again, like the price we're going to pay for kind of the nice, like, there's nice intuition behind these models. They're very general. They're very like expressive models we're going to see. The downside is going to be that there are situations where these are provably not optimal. Okay? Like there are going to be situations where there are methods for doing things like community recovery and estimation, and these will not achieve the optimal rate. And if time allows, on our last day, I'll talk about recent work by myself and one of my students on that. No promises, because I'd rather talk about other people's work. It's more interesting than mine. But like, if time allows, I'll show an example of where we start with a spectral method. The spectral method is suboptimal, and then we show how to fix the spectral method to get back to optimality. That's if time allows. Other questions? How about thank you all very much, and I'll see you at the coffee room.